Hello, everyone. I'm very excited to be here to share our work on normalizing the metagenomic HiCzin data and detecting the spurious context using zero-inflated lecture binomial regression. This work was accomplished by Yuxuan Sarah, Judd Foreman, and Fengzhu Zhang from University of Southern California. Let's begin with the metagenomic HiCzin analysis. In the metagenomic region, we want to characterize the diversity of species from microbiome samples. Traditional metagenomic shotgun sequencing technologies directly capture the genomic fragments and generate a large number of short reads. These shotgun reads are then assembled into longer contigs. Recently, HiCzin technique has been used in the metagenomics region to construct the relationships between assembled contigs. Specifically, metagenomic HiCzin is a genomic proximity negation technique, generating millions of paired end reads linking metagenomic sequences in close three-dimensional distance within cells. Therefore, the number of HiCzin read pairs collecting two assembled contigs is related to the probability that the contigs belong to the same genome. This property results in multiple downstream analyses, such as contig clustering and various host interaction probing. However, there exist strong experimental biases for the number of HiCzin interactions between contigs. Here we report on two types of biases with substantial influences on metagenomic HiCzin contact counts: the explicit biases and implicit biases. Explicit biases include three potential factors: the number of restriction sites on contigs, the length, and the coverage of contigs. Actually, all the explicit biases can be observed. Implicit biases contain unobserved interactions and spurious interspecies contacts. Unobserved interactions are chimeric DNA fragments that are missed due to factors such as the mappability of the contigs and constraints on accessibility. Spurious interspecies contacts arise from the negation of DNA fragments between closely related species and will confound the interpretation of the HiCzin data. As implicit biases are unobservable, it is challenging to detect and correct implicit biases. Then we will validate these two types of biases on a public metagenomic yeast sample consisting of 13 species. The first type of biases is the explicit biases. These three figures show the explicit biases of the raw HiCzin interaction counts. The y-axis of all three figures represents the non-zero contacts for the contig pairs from the same genome, or say the non-zero intraspecies contacts. And we refer to the non-zero intraspecies contacts as the valid contacts. The x-axis of each figure is the product of one factor of the explicit biases. Valid contacts were enriched between pairs of contigs with a high number of restriction sites, long contigs, and contigs with high coverage. And the Pearson correlation coefficients between raw valid contacts and the product of the number of restriction sites, the length, and the coverage for each pair of contigs were 0.429, 0.4, and 0.184 respectively. This demonstrated that these three factors were indeed highly correlated with valid contacts. As for the implicit biases, one remarkable phenomenon for intraspecies contacts was the presence of excess zeros, which means zero contacts account for a large proportion within intraspecies contacts. Specifically, the number of valid contacts only made up 14.9% within all intraspecies contacts. Moreover, the number of spurious contacts made up 25.5% of all non-zero contexts, which could confound the interpretation of the HiCzin data in the downstream analysis. Therefore, it is necessary to normalize the HiCzin data. And actually, we have two goals for the normalization: correct the explicit biases and remove the spurious interspecies context. In order to correct both explicit and implicit biases, we put forward a new normalization method based on the zero-inflated generalized linear mix framework. We first assume that the interspecies context follow the zero-inflated lecture binomial distribution, which is a two-component mixture model combining a max point at 0 with a count distribution. Here for the count distribution, we use the lecture binomial since the raw metagenomic HiCzin interaction counts suffer from serious over dispersion. And mathematically, let Y denote the population of the interspecies context, and Z denote a corresponding zero-inflated random variable. Here Zij is the random variable of HiCzin context between contig I and contig J, consisting of two components. It can be equal to 0 with probability πj, or follow the lecture binomial regression distribution with probability 1 minus πj. And actually πj here can be explained as the probability that the context between contig I and contig J cannot be observed. Normally, in the generalized linear model, we use the link function to connect the distribution parameters and the potential features. In our model, we assume that μij and πj are related to three factors of explicit biases by the log link and the logistic link, respectively. Therefore, we can obtain the final regression equation. All the unknown parameters in the regression are estimated by the maximum likelihood method using the R package GRMM-TNB. After regression has been solved, the residues of the counting part will then serve as a normalized metagenomic HiCzin context. And in this way, we can correct all three factors of explicit biases while taking the unobserved interactions into account. After correcting the explicit biases, our second goal is to remove the spurious context. Before we introduce the methods, which is still based on our regression model, we can first observe the difference between the valid context and the spurious context as these four figures. The first figure tells us that compared with the raw valid context, the average value of raw spurious context was much smaller, while the rest of three figures show that the average number of restriction size, length, and coverage of contigs was significantly larger for spurious contexts. This evidence indicated that spurious contexts were more likely to be generated for longer contigs with more restriction size and higher abundances. Therefore, we expect that the magnitude of the normalized spurious context by the factors of explicit biases to be significantly smaller than that of the normalized valid context. Therefore, a basic idea is to discard the normalized context whose values are less than a selected threshold as the spurious context. Specifically, we design a hybrid statistical model and define two metrics. The enrichment score of context is defined as a log ratio of observed context and expected context between the contig I and contig J. We also define the p-value, which is the probability that Yij is less than Oij. Note that Yij here follow the lecture binomial regression or distribution according to our assumption. And the parameters for the distribution has been estimated by our regression model. And then we choose the cutoff for the enrichment score and p-value, while contexts below the threshold are regarded as the spurious context and then discarded. We determine the threshold such that less than a certain pre-selected percentage of valid contexts are incorrectly identified as spurious contexts. Then we apply our method to the metagenomic yeast dataset. After normalization, the distribution of normalized spurious contexts deviated to the left from the distribution of normalized valid contexts, facilitating the distinction from spurious context to valid context. As we need to pre-select a percentage reflecting the acceptable fraction of losses of the valid context, we can observe that the threshold increased with the pre-selected percentage. And the larger threshold could detect more spurious contexts while incorrectly identify a higher number of valid contexts. Though there existed a trade-off, the proportion of discarded spurious contexts increased much faster than that of discarded valid contexts, indicating that we could remove a large fraction of spurious contexts while keeping most of the valid contexts. To evaluate the capability of normalization methods to detect the spurious context while retaining the valid context, we designed the discard retain curve as the third figure. The x-axis is the proportion of discarded spurious contexts among all spurious contexts, and the y-axis represents the proportion of retained valid contexts within all valid contexts. We denote the area under the discard retain curve as AUDRC, and AUDRC will then be used to evaluate the performance of spurious context detection. We compare our HiCzin method with other metagenomic HiCzin normalization methods. The naive methods mean that we directly divide the raw context by one factor of explicit biases. Being 3C norm is a two-step normalization method. It first divided raw HiCzin context by the product of the number of restriction sites, and then used the light-Lewis algorithm to construct a general Bayes stochastic matrix after the first step correction. Naive lecture binomial method is similar to our HiCzin normalization method, but use the lecture binomial regression and ignore the excess zeros. We can see that our HiCzin method has a better performance than all other methods for both correcting explicit biases and detecting the spurious contexts. Okay, so let's make a conclusion. In this presentation, I put forward two types of biases for the metagenomic HiCzin data: explicit biases and implicit biases. Explicit biases include the number of restriction sites, contact length, and contact coverage. Implicit biases include the unobserved interactions and spurious interspecies contexts. To solve the problem of the biases, we put forward a new normalization method, HiCzin, which is based on the zero-inflated lecture binomial regression framework. And we also validate that the HiCzin normalization method has a better performance than other methods on normalizing the metagenomic HiCzin data and detecting the spurious interspecies context. Okay, thanks for the listening. Any questions?